In 2015, Hubble pointed at a set of coordinates in a galaxy 22 million light-years away and found nothing there. Not a dimmed star, not a fading ember, nothing. 6 years earlier, that same position held a red supergiant with roughly 25 times the mass of the Sun. A star so wide that if you dropped it where our Sun sits, it would swallow the orbit of Jupiter. Physics says a star like that dies in a supernova. It should have outshone every star in its galaxy combined for weeks. Instead, it flickered once, faintly, and went out. Here is the part that should bother you. The survey that caught it was built by astronomers who expected to find 0 of these. They found 1 almost immediately. By the end of this, you will understand why they call it an unnova, and why the number matters more than the star. The object has a catalogue name, N6946BH1, and it lived in NGC 6946, the galaxy nicknamed the Fireworks Galaxy, because it produces supernovae faster than almost anything else in our neighborhood. That detail is not decoration. Astronomers were watching that galaxy precisely because they expected explosions there. What they recorded instead was strange from the beginning. In 2009, the star brightened to about 1 million times the luminosity of the Sun, and held that brightness for a few months. By supernova standards, that is nothing. A real core collapse supernova reaches something closer to 1 billion solar luminosities. This was a whisper where a scream should have been. Then the whisper stopped. Over the following years, the star faded below the detection limit and stayed there. Follow-up imaging found no expanding debris, no glowing remnant, no shockwave lighting up the surrounding gas. Just a faint infrared smudge, consistent with dust, sitting where 25 solar masses of star used to be. Now think about what that means physically. Mass does not vanish. If the star did not explode, the material did not go anywhere. It went down. That is the standard reading of the event, and I want to be careful here because this specific object is genuinely contested, and we will get to the argument against it. But set the single star aside for a moment, because the star is not the thesis. The thesis is this: we cannot look at a massive star and tell you how it will end. The models disagree with each other and with the sky. And the entire visible history of the universe, every catalogue, every survey, every textbook chart of stellar death, is assembled almost exclusively from the deaths that were loud enough to be seen. The quiet ones left no record at all. Before we go further, I am curious where you are watching from and what time it is there. Put your city in the comments. And tonight, if the sky is clear, go outside, look up for 30 seconds, and ask yourself honestly whether you would notice if one of them stopped being there. You would not. Neither would I. Neither, for a long time, would anyone. When this result reached the public in 2017, the headlines were clean and confident. A star collapsed into a black hole. Astronomers watched it happen. The story arrived pre-packaged as a discovery, which is a comfortable shape, because a discovery means somebody found something and the system worked. Read the actual papers and the language changes completely. Kucharnik, Adams, Gurka, Stanek, and their colleagues wrote about a candidate. Consistent with, likely. The survey itself has a blunt name in the literature, the search for failed supernovae, and its whole design admits the awkward thing underneath. They were not hunting an object. They were hunting an absence. Here is why that distinction matters more than it sounds. Astronomy is built entirely on things that emit. Every instrument we have, optical, radio, infrared, X-ray, is a device for catching something that arrives. We have no detector for a thing that stops. To find a star that failed to explode, you cannot point at it. You have to photograph a galaxy for years, catalogue every star bright enough to resolve, come back, and check whether anything on the list is missing. That is not observation. That is bookkeeping against loss. And bookkeeping is slow, unglamorous, and almost impossible to fund. So the public version had to be a discovery, because the honest version has no ending yet. The honest version says we ran the ledger on a few dozen nearby galaxies, and after roughly a decade, we came up short by one star. And we do not fully understand why. And we are not certain what happened to it. That is not a headline. That is an open wound in the model. Now hold both versions in your head at once, because this is where the reassuring frame begins to break. The reassuring frame works only if the star's disappearance is an oddity, a footnote, a single weird object in a single weird galaxy. It stops working the moment you ask how a star that massive could possibly skip the most violent event in the modern universe. To answer that, you need one fact almost nobody outside astrophysics knows. The explosion you picture when you hear the word supernova is not the event. It is the residue of the event. 99% of a supernova is invisible. A massive star spends 10 million years building a metal core it cannot use. Hydrogen fuses to helium, helium to carbon, then oxygen, neon, silicon, each stage faster and hotter than the last, until the center is iron. Iron is the end of the line. Fusing it consumes energy instead of releasing it. The furnace that held the star up for its entire life switches off. What happens next takes less than a second. The iron core, about 1.4 times the mass of the Sun, packed into something the size of Earth, collapses inward at speeds approaching 70,000 kilometers per second. A quarter the speed of light. It falls until the atomic nuclei themselves touch, and then it slams to a halt and bounces, launching a shockwave outward through the infalling star. And that shockwave stalls. Every modern simulation shows it. It plows into the mass still raining down, loses energy, and dies about 150 kilometers out. So what actually blows the star apart? Neutrinos. The collapse releases roughly 10 to the 46th joules. Written out, that is a 1 followed by 46 zeros. Compare it to something you can hold. Our Sun, burning steadily for 10 billion years, will radiate about 1% of that number across its entire existence. A dying star produces roughly 100 suns worth of lifetime output in about 10 seconds. 99% of it leaves as neutrinos. About 1% goes into kinetic energy, the actual blast. 1/100th of 1% becomes light. Let that sit. The supernova you can see, the thing that briefly outshines 100 billion stars, is the rounding error. When SN 1987A went off in the Large Magellanic Cloud, something like 100 trillion neutrinos passed through every human body on Earth. Through you, through the floor, through the mountain behind you, through the entire planet as if it were not there. Nobody felt a thing. Nobody knew until the light arrived hours later. Now here is the mechanism that matters. A fraction of that neutrino flood, well under 1%, gets absorbed by the material behind the stalled shock. It heats that material. It repressurizes it. If enough energy deposits fast enough, the shock revives and the star explodes. If it does not, the shock keeps stalling, matter keeps falling, and the core grows past the mass a neutron star can support. Read that back slowly, because it reverses everything. The explosion is not what a dying star does. The explosion is a rescue, powered by the least interactive particle in physics, that has to work within about 1 second. And now the obvious question: what happens on the nights it doesn't? Most people carry a simple rule in their heads. Small stars fade quietly. Big stars explode. Bigger star, bigger bang. That rule is wrong. And the way it is wrong is worse than if it were simply backwards. Whether a star explodes does not depend on its mass in any clean way. It depends on how the mass is arranged in the final hours. Theorists measure this with a quantity called compactness, introduced by Evan O'Connor and Christian Ott in 2011. Strip away the math, and it asks one question. When the core collapses, how much material is stacked directly on top of it? And how fast is that material falling in? If the layers above the core are thin and spread out, the neutrino rescue has room to work. The shock revives. You get a supernova. If those layers are dense and heavy, they rain down faster than the neutrinos can push back. The shock never recovers. The core keeps eating. It crosses the limit a neutron star can hold, around 2¼ solar masses, and an event horizon closes over the whole thing while the outer star is still falling. Same physics, almost the same star, opposite ending. Now here is the part that should genuinely unsettle you. When you run this across a range of stellar masses, the outcome does not sort itself into a tidy line with explosions below and collapses above. It scatters. Modern models from groups like Suchbold, Ertl, and Woosley produce what the field calls islands of explodability, patches where stars blow up sitting right next to patches where they do not, interleaved across the same mass range. Move a star from 22 solar masses to 23 and the prediction flips. Change the assumed rotation, or the metal content, or the convection treatment, and it flips again. Let me be fair, because this is where the sensationalists cheat. This is not evidence that astrophysicists are incompetent. It is the opposite. Those jagged maps exist because the models got detailed enough to stop lying. The earlier, smooth picture was smooth because it was cruder. But the honest consequence is still brutal. Point at any massive star in the night sky. Betelgeuse, Rigel, Antares, any of them. Nobody on Earth can tell you how that star ends. Not the year, which is understandable. The mode of death itself. We built an entire cultural image of stellar death, the exploding star, the seeding of the galaxy, out of a process we now know can silently fail. And if it fails invisibly. So the only question left is how often. That answer is already sitting in the data, and it is not small. There is a way to test this without waiting around for stars to die. Go backwards. When a supernova is spotted in a nearby galaxy, astronomers pull the archives. Hubble and the big ground telescopes have been photographing these galaxies for 30 years. So you find the explosion, go back to old images of that exact pixel, and identify the star that used to be there. It has been done dozens of times now. It is one of the most direct tests in stellar astrophysics, and it fails at the top end. Stephen Smart and colleagues assembled these progenitor identifications and found a ceiling. The stars caught in the act of exploding cluster below roughly 17 or 18 solar masses. Above that, they mostly are not there. Yet we can see red supergiants in our own galaxy and the Magellanic Clouds at 25-30 solar masses. They exist. They are the brightest stars in the sky. They just never seem to be the ones exploding. The field calls this the red supergiant problem, which is a very polite name for a hole in the census. Now stack a second measurement on top of it. Count how fast the universe forms stars, calculate how many should be massive enough to core collapse, and compare that to how many supernovae we actually observe. That comparison has been run repeatedly. The observed rate comes in low, by something close to a factor of 2. 2 independent methods, same direction, missing deaths. The failed supernova survey put a number on it. Watching roughly 24 nearby galaxies for over a decade, the collaboration estimated that somewhere around a sixth of massive stars may end without an explosion. The honest uncertainty is wide, running from a few percent up toward a third. and I am not going to pretend otherwise. But take the lowest end, and it still breaks the picture. Even 5% means the story we tell about stellar death has a silent chapter that no telescope has ever meaningfully sampled. Here is the scale rupture. This is not one weird star in one weird galaxy. Massive stars die constantly. In the Milky Way alone, core collapse happens roughly once or twice a century. Run that back across the 13 billion years our galaxy has existed, and you are talking about a population of quiet endings numbering in the millions, none of which announced themselves. And every single one of those stars was carrying something. Because a massive star is not just a light source, it is a factory, and it spent its entire life manufacturing the specific atoms that a supernova is supposed to deliver. If there was no supernova, then nothing was delivered. Take a breath. Hold it for a second. 65% of your body by mass is oxygen. Another 18% is carbon. There is roughly a kilogram of calcium in your skeleton and about 4 grams of iron in your blood right now. Enough for a small nail. None of that was made on Earth. None of it was made by the sun. Our sun is too small and too young. Those atoms were forged in the cores of massive stars, in fusion stages lasting centuries, then months, then days. And the reason any of them are outside those stars is that the stars blew apart and threw them out. That is not poetry. That is a supply chain. Every element heavier than helium in your body was delivered by stellar death, and the delivery mechanism is the explosion. So now apply the failure mode. When the rescue fails and an event horizon closes over the core, all of that manufactured material, the oxygen shell, the carbon, the silicon, the freshly built calcium, falls inward and crosses a boundary that nothing returns from. Not slowly, not partially. It is removed from chemistry entirely. I want to be precise because this is where it gets subtle rather than absolute. Something does escape. As the core radiates away a few tenths of a solar mass in neutrinos, the star's own gravity weakens slightly, and that tiny change can shove off a thin outer layer of hydrogen. That is the leading explanation for the faint, months-long glow recorded in 2009. A star with 25 solar masses of material sheds a wisp of unprocessed hydrogen, gives off a whisper of light, and takes everything valuable down with it. And the whisper is the receipt. It tells you the delivery was cancelled. Now make it local. Betelgeuse sits about 548 light-years away, somewhere between 16 and 19 solar masses, sitting on Orion's shoulder in a sky humans have navigated by for thousands of years. In late 2019, it dimmed enough to make headlines worldwide, and people genuinely wondered whether they were about to watch a star die. Picture the version nobody talks about. No blast, no months of daylight visible brilliance. Orion's shoulder simply fades over a season, flickers faintly, and is gone. No wreckage, no expanding shell for future telescopes to study. Just a permanently altered constellation and no explanation visible from here. That is what makes this category of event different from every other catastrophe in astronomy. It leaves nothing behind to examine. Which raises the only question that actually matters for detection. If the light barely changes and the debris never arrives, how would we know it happened at all? There is exactly one way to watch a black hole being born in real time. and it has nothing to do with light. Remember that 99%. When the core collapses, the neutrino flood starts within milliseconds, long before anything visible happens at the surface. In a successful supernova, that signal swells and then tails off over roughly 10 seconds as the new neutron star cools. In a failed one, it stops. Not fades, stops. The horizon forms and the source is cut off mid-signal, like a phone line going dead in the middle of a sentence. That truncation is the signature. It is the only direct evidence a black hole is forming that can reach us as it happens. So who is listening? In February 1987, a star died in the Large Magellanic Cloud, 168,000 light-years away. Something like 10 to the 58th neutrinos left that star. 3 detectors on Earth caught 25 of them. 25 particles across 13 seconds. And that handful remains the foundation of everything we claim to know about how core collapse actually proceeds. 39 years later, it is still the only one we have ever caught. The instruments are better now. Super Kamiokande is 50,000 tons of ultra-pure water, sitting a kilometer under a Japanese mountain, and it would register thousands of events from a supernova in our own galaxy. There is an alert network, S-News, designed to warn the world's telescopes hours before the light arrives. Juno, June, and Hyper Kamiokande are coming online to sharpen the timing enough to actually see a signal cut off. But sit with the dependency for a moment. Our entire real-time window onto stellar death is a few buildings full of liquid, buried under rock, run by a handful of collaborations, funded on cycles measured in years. That is the whole apparatus. That is our species' entire ability to notice. And the optical search is worse. To catalogue failed supernovae, you have to photograph the same galaxies year after year, maintain the star lists, and wait for a name to drop off. The survey behind this story ran for over a decade to produce one candidate. No paper announces a discovery every season. There is no dramatic image. Funding committees work in 3-year blocks, and the scientific reward system pays for things that appear, not for things that stop appearing. We built an entire observational culture around detecting arrivals. Absence has almost no institutional constituency. Which brings us to the language. Because when the evidence is this thin and the stakes this large, scientists get extremely careful with their words. That caution is correct. It is also the reason none of this reached you. In 2024, the James Webb Space Telescope looked at those coordinates, and the story got complicated. Webb sees infrared with a sharpness nothing before it could match. Where earlier instruments recorded one faint smudge, Webb resolved the position into multiple separate point sources. Emma Beezer and colleagues published an analysis arguing that the leftover glow fits something other than a black hole shrouded in fallback dust. Their preferred reading is a stellar merger, 2 stars spiraling together into a remnant wrapped in dust, which would also explain a modest months-long brightening in 2009. If they are right, the most famous failed supernova candidate in astronomy is not a failed supernova. I am telling you this because you should hear it from the same voice that told you the rest. Other researchers, including the original team, have pushed back, and the case is not settled. That is what a live scientific argument looks like. So let me be direct about what I am not claiming. I am not claiming a cover-up. I am not claiming anyone lied or fudged an image. I am not claiming the researchers were sloppy. Every hedge in those papers, every candidate inconsistent with, was written by people doing the job properly. Here is what I am claiming. Notice what the careful language actually accomplished out in the world. The 2017 result traveled everywhere as a clean triumph. Star becomes black hole. Astronomers watched it happen. The 2024 challenge barely traveled at all. And the finding underneath both of them, the one that never made a headline in either direction, is that we ran a decade-long census of stellar death in nearby galaxies, and the books do not balance. That is the pattern. The dramatic object gets attention. The structural gap does not. Because a gap has no picture, no press conference, and no narrative shape. And now the part that survives the dispute entirely. Delete N6946-BH1 from the record. Pretend it was a merger, or a dust cloud, or an error. The red supergiant problem does not move. The progenitors above 18 solar masses are still missing from the archival images. The observed supernova rate is still low against star formation by roughly a factor of 2. The models still produce jagged, interleaved islands of explodability. The neutron star mass limit still exists, and stars still exceed it. One object is contested. The hole in the census is not. That is the difference between a story about a star and an argument about the sky. And it is why this cannot be filed away as a curiosity. Because we can now point directly at what the missing deaths produced. They are in our own neighborhood. For most of the last century, we only found black holes when they were eating. Every classic detection worked the same way. A black hole pulls gas off a companion star. The gas piles into a disk. Friction heats it to millions of degrees, and it screams in X-rays. That is not the black hole. That is the food. We were never cataloging black holes. We were cataloging appetite. Then Gaia changed the method. It measures the positions of more than 1 billion stars precisely enough to see them wobble. And a wobble means something massive is pulling on them, whether or not that something emits anything at all. In 2022, that method found Gaia BH1, roughly 10 solar masses orbiting a perfectly ordinary sun-like star about 1,560 light-years away. Astronomically speaking, that is next door. It emits nothing at all. It had been sitting quietly out there the entire time humans have had telescopes. In 2024 came Gaia BH3. Around 33 solar masses, roughly 2,000 light-years out, the heaviest stellar black hole yet found in our galaxy. Now the number that reframes everything. Models suggest the Milky Way contains on the order of 100 million stellar mass black holes. We have confirmed a few dozen. And here is the sentence I want you to sit with. Not one of those objects, not a single one anywhere in the sky, has ever been observed forming. Every black hole we know about was already finished when we found it. We have inferred the process, simulated it, written it into textbooks, and never once witnessed it. Gravitational waves widened the problem rather than solving it. When LIGO detected its first merger in 2015, the black holes were about 36 and 29 solar masses, heavier than the population of remnants astronomers comfortably expected from ordinary supernovae. Later detections went heavier still. The universe is producing dark, massive objects at rates and masses our death models did not cleanly predict. So step back and look at the shape of the whole thing. Our map of the universe is not a record of what exists. It is a record of what radiates. Every catalogue, every survey, every deep field is assembled from objects that had the courtesy to send us photons. Physics edited the map before we ever started drawing it. The failed supernova is not a curious footnote in that map. It is the mechanism by which the map gets edited. It is the exact moment a large, real thing exits the observable universe without leaving a signature. Which forces one final question, and it is bigger than any single star. What is the night sky actually a record of? Let me put the case together, because every piece of it is measured, published, and contested in the open. The explosion is not what a dying star does. It is a rescue attempt powered by neutrinos that has to succeed inside about 1 second. Whether it succeeds depends on the arrangement of matter above the core, and the models that map this produce jagged, interleaved outcomes rather than a clean threshold. The most massive red supergiants are missing from the archives of exploding stars. The observed supernova rate falls short of what star formation predicts by roughly a factor of 2. Silent black holes are being found in our own neighborhood, and not one of them was ever seen forming. Every one of those statements stands on its own. Together, they say something the field states carefully and the public has never absorbed. Here is the comfort I want to take away from you before we finish. It is the assumption that we would notice. We assume the universe is loud when it does something enormous, that mass and violence produce a signal, that the death of a star with 25 times the mass of the Sun is the kind of thing a species with telescopes would obviously catch. For this class of death, there is nothing to catch. No blast, no remnant, no expanding shell, just a star that is present in one image and simply absent in the next. And 22 million years later, a graduate student runs a list and finds a name with no light attached to it. Now go back to that 2015 frame from the beginning, the empty coordinates, the nothing. Read it again with everything you now know. That is not a missing star. That is not a failure of the telescope or a gap in the data or a mystery waiting for a better instrument. That is what a birth looks like when it goes correctly. There is one real reason for hope, and it is recent. On June 30th, 2026, the Vera Rubin Observatory formally began its 10-year survey, scanning the entire southern sky every few nights and generating millions of alerts. Its whole architecture is built around change, including things that get fainter. Meanwhile, Juno, Dune, and Hyperkamiokande are being built to catch a neutrino signal that stops. For the first time, we have instruments designed to notice absence. So the next one probably will not go unwitnessed. That matters enormously. But understand what that means. We are about to find out how often the universe deletes something this large without an announcement. That number does not exist yet, and we are only now building the eyes to count it.